we're going to mess around with some light sticks. We're going to mess around with the chemistry of light sticks. I don't know if this is going to work or not, but we're going to give it a shot. Yes, indeed, we are. So let's see, light sticks. Where's my PVC cutter so I can break these things open? Here it is. Okay, here we go. Let's see. I just want to see what this looks like. Let's get this thing going. Oh, yeah. Let's turn the lights off. That's cool. I'm not eating a light stick, Isaiah. I'm just going to try to fiddle around with them. It's going to be a little tough today because I'm in the dark. I turn this back on so I can find my clipper. Here we go. How you doing there, Rage? We're going to mess around today with the chemistry of light sticks. You can see here I have a blue light stick. I'm going to use these PVC cutters. We're going to try to get this thing open and see what happens, all right? Isaiah, I'm doing different stuff because you've said you wanted to see different stuff, so that's what we're going for today. So right here, I'm going to take some PVC cutters. I hope I don't make a mess. We're going to try to open this thing. I think I did okay, yeah. We got the top off. And now we're going to pour the glowing fluid into this Erlenmeyer flask. Come on, baby. That's just beautiful. Yeah? Sure it is. And what I'll do is I'm now going to take, the used light stick stuff here, and I'm going to place that in an empty bottle, which is what I'm going to use for my trash. Let's see. This will work. It's going to work right here. Got my empty bottle. And it goes. So, Leighton, what's happening is I just took a light stick and I cut it open. And I poured the fluid into this flask right here. And then we're going to mess around with it. So one thing that's interesting about the chemistry of light sticks is it's catalyzed by a base. Here, we'll put this in the back so you can see where I put the used light stick in this bottle. So yeah, thanks there, Rex. So what's interesting about light sticks is they're catalyzed by a base. So you can see I have some light stick mixture in here. I don't know if the camera's going to pick this up, but what we're going to try is I'm going to add some base to this fluid, and it should catalyze it. Unfortunately, I think the camera's going to adjust. So I'm going to need a control. Yeah, let's see what I can do for my control here. Excuse me, I'll get let me get a control cup. Is this going to work? Nope, I got to get another one. You have to forgive me, this is the first time I'm trying this, so there's going to be a few glitches with what I'm doing today. Okay. This will work as our control. All right. So let's get another one going back here in the back. So we'll get this light stick going here. By the way, a light stick, it's powered by, no, this is all just, straight up organic chemistry. This isn't any microbes going on here. So what powers a light stick is the reaction between hydrogen peroxide and a molecule. I'm from the United States, Umer. And a molecule called trichlorophenoxylate. And when those two react, they release an enormous amount of energy. And we can talk about this maybe in a little bit, but that energy ends up going into dyes that are contained in the light stick. And those dyes, when they get that energy, they release the energy as light. And one of the products of the reaction is carbon dioxide, believe it or not. We'll just pour a little bit of light stick mixture in here. We'll put a bunch in the back here too. That's our control there in the back, okay? Energy turns into light. That's probably you're right there, Big Z. If we're getting down to the molecular details, we're going to have to get a little more specific, but, we can skip that for now. And then, the way you get different colors, you just stick different dyes in the light stick. That's all. So just like different colored markers have different colored dyes that give you different colors, different dyes in the light sticks are going to give you different colors. Now, what I'm going to try, here's my control. I'm not going to add anything to this. I've never done this live before, on a live with a camera, so I don't know how the light is going to pick this up. However, we're going to give it a shot. I'm going to add some base. Thank you, they're out of connection. I'm going to add some base, which is known to catalyze the reaction. And a catalyst just, it speeds up a chemical reaction. It participates in it, but is not consumed. So here we go. We're going to just start adding some base to this. Let's see what happens. All right, here goes the base. Couple drops. I can't tell if it's getting brighter or not. It's probably because it's not mixing real well. Oh, yeah, sure. What do y'all think? Did that get brighter? I think it did. What do you think? I mean, it is, here's the control back here. So you got to understand the camera is going to adjust, right? The camera is going to adjust the amount of light that you can see because it's going to try to keep everything looking nice and pretty. But just notice how much more brightly this is glowing in comparison to this in the back. Okay, thank you, Big Z. I appreciate you all letting me know what you're seeing. And now what I'm going to do is I'm going to add the opposite of a base, which is an acid. Hello there, Saki-ga. So that should neutralize the base. And since there won't be any base present, that's the reaction won't be going quite as quickly. So now I'm going to add some acid to this mixture. Here we go. I'm adding drops of acid right now. And let's see what happens if I add the drops of acid. It's going to take a bit. In goes the drops of acid. Let's give it a swirl here and see if it gets less bright. Thank you there, Big Z. So I'm going to give it a swirl. And look at that. You can certainly tell, as now that I've added the acid, actually, it's kind of looking like the one in the back is just about as bright, if not brighter. The control is now just as bright, if not brighter, than the flask to which I added the acid. Let's see if we can reverse it again. So I'm going to go ahead and add base. Again, I've never done this live. I'm glad it's working to some extent. There we go. Let's add a bit of base now and see what happens. Thank you there, Game Pro. Thank you there, Big Z, for letting me know. Thank you there, Big Z. In goes the base. Oh, looks like my base has a plug in it. Let's add this bottle here. Let's add a couple drops. Okay, I added quite a bit of base there. Let's give it a swirl and see if it can't recover the brightness. I may have destroyed I think I may have destroyed the compound. Sure enough, you can see this is now not glowing at all. So I probably destroyed everything. You know what I probably did is I probably just added acid, which indeed I did, which is why it went out. Idiot me, I added the wrong stuff. So let's try this again. I'm like, why isn't it working? Why did it go out? Well, that's because, hey, thank you there, User Brain. Appreciate that. So yeah, what happened here is like an idiot, I added acid to this and, that completely stopped the reaction. Let's see if we can reverse it by adding base back. I'm adding quite a bit. You can hear it. Come on, are we going to recover? Are we going to recover? Come on, baby. Are we going to? I'm seeing a little bit to my eye. I'm seeing a little bit of blue color start to, the chemiluminescence is starting to take off again. But I think the acid may have destroyed everything. I think we might have done this a little too much. I'm going to keep trying. There's a bunch of base. I think I did too much. Is it getting hotter because the beaker looks like it's fogging? Yes, it is getting hotter, but that is probably most likely coming from the reaction between the hydrochloric acid and the sodium hydroxide that I added. So that's why you're seeing the, that's why you're seeing the fogging. It's from the reaction between the hydrochloric acid and the sodium hydroxide. We're going to try this again. So just give me a second. Hey, thank you there, Game Pro, for the subscription. I appreciate that. We're going to give this another shot. So I'm going to just pour some of this into this container here. We're going to give it another shot. Try her again. I'm going to rinse down the sides just a bit so we can try this again, okay? All right, rinse down. I'm going to turn on the light here so I can see what I'm doing. Give me a second here. You can still see that one in the back is still glowing. And while I'm, while I'm cleaning everything up here, oh, curses. I'll show you here the chemical reaction that powers a light stick. You can see there that large molecule here we call this trichloro for 3 chlorines. You see 3 chlorines here. Trichlorophenyl oxalate. So this is a special type of molecule. This is where a lot of the energy comes from. It's going to react with hydrogen peroxide, and then what happens is you kind of snip this in pieces. You get 2 kind of these end pieces fall off. It's a type of phenol. They add the chlorines to this molecule because just plain phenol without the chlorines on there is quite toxic. So that's why they put the chlorines on there. And then what happens is sort of this middle part, you see these oxygens here, they snap into place, and they make this funny-looking species. We call this dioxetane dione. You don't need to know that. You just can think of it as a high-energy form of 2 carbon dioxide molecules stuck together. All right? That's sort of the first step. So this is a pretty cool thing when people finally figured out that this is what was going on. Anyways, we'll just call it the high-energy double CO2. What happens is that high-energy double CO2, it reacts. It actually slams into some di molecules, and it splits it into 2 molecules of carbon dioxide, and then the di gains energy. And the way we signify that is we just put a little asterisk here to say, hey, some energy as a result of this collision went into the di molecules. And then we say that the di molecules are excited. The electrons in it are excited. And those excited electrons, they don't stay there forever. They go back down to their lower energy state. But because, the di has lost energy in this process, it's got to give that energy off as something, and it gives it off as light. That's it. Thank you there, Macer. Hello there, King JJ. And then, and different dyes give you different colors. That's it. That's the whole idea. So I think I've got this thing rinsed at least. So we're going to give it a shot again. What in the organic chemistry is going on? Well, I'm no organic chemist. I'm definitely no organic chemist, but I know a little bit about light sticks, and that's what we're playing around with. So we're gonna try this again with another light stick. So let's get this one going here. And that reaction I just showed you is happening here. And then I don't know if this is going to work, but we're going to give it a shot, okay? So you notice I said that different dyes give you different colors. And I happen to know, they're just different fluorescent dyes. And I happen to know that there's a molecule in here called phycocyanin. You might be able to see it. It's actually blue-colored dye, but you might see a little bit of red, and that's because this molecule, when it gains energy, in this case it's getting energy from the light here in my room, when it gets some energy, it gives off a red color. So even though the dye is blue in color, it fluoresces red, which is why this might look like it's a little bit, violet rather than just straight blue. And we're going to see if I don't know if this is going to work. I've not tried this before. We're going to go ahead and just add a few drops of this dye that contains phycocyanin to our flask here. All right. So you can see it's blue in color. Oh, man, I hope this works. This would be so cool if this works, man. This would be so cool if it works. Hey, Roy the Chemist. We got another chemist here. Just want to say I really enjoy your video. Hey, thanks there, Roy the Chemist. Let's connect, all right? I would love to be able to see some of your stuff. So, make sure you send me a note so we can get connected there. All right. Sorry there, Charlie. I hope I'm not keeping you up. I'm going to open this light stick now with a pair of PVC cutters. I'm going to try to do this so I don't make a mess. There we go. I got the top off. And the dyes that are contained in this light stick, they happen to be quite a few of them because, to get white light, you need all the colors of light. So you need a bunch of different dyes in here giving off light so that you get white light, right? But what I'm trying to do here with this blue dye that I added here, I know it fluoresces a red color, and I'm hoping, again, I don't know if this will work because I haven't tried it, but I'm hoping that when I pour this in here, we might see some red fluorescence. And I'm thinking it's a bust. I don't think it worked. I'm going to maybe try to add a little more just for the heck of it. Maybe just for the heck of it, but I don't think we're going to get some phycocyanin fluorescence. I'm not seeing evidence of it. That looks very white still to me. I'm not seeing any evidence of red, which is a bummer for me, but hey, that's, it is what it is. The nice thing about science is you can't really have a failed experiment. You just have new observations. So I've got a new observations here. My new observation is that in this particular experiment that I like to do, phycocyanin does not seem to fluoresce red in the presence of light stick mixture. I'm glad to hear that, Charlie. Roy, you can just send me you should be able to find my email if you go, to my page. It's just tommytechnetium@gmail.com. So yeah, you can see here we've got some light stick mixture that's blue. You can see here some light stick mixture that's white. I'm going to try just a few other dyes just for the heck of it. I'm going to add some curcumin, which is a yellow colored dye. I don't know if this will glow a different color, but we can sure try. I'm going to add a few drops here just for fun, just to see if we get a different color fluorescence than that. I'm not seeing a color. Whoa, baby, I see a little bit of color shift there. I'm seeing some green, man. Come on now. I don't know if you're picking that up. But sure enough, I am noticing some green fluorescence. Come on, baby. Come on now, that's cool. So it looks like the curcumin, there's a molecule in this particular dye that is it's a main ingredient in turmeric, and it does indeed fluoresce. I'm a little surprised to see a green color. I don't know if curcumin fluoresces green, but it sure looks like it's fluorescing like a yellow-green in this particular experiment. So what I just demonstrated to you is the fact that different colored dyes in our light sticks do indeed give you the different colors. And I did that by just adding a little bit of this particular dye here. By the way, the dye I added is just these natural food coloring. I didn't use the regular food coloring. I know that these dyes tend to fluoresce pretty well. I used the yellow version. I gave it a shot of the yellow. Man, that's cool, baby. Come on now, that's cool. Let's add another drop here. I'm so excited that worked. We'll give it another drop, see if we can make it a little more green. Hello there, Peter. Oh, I'm so sorry you are all not quite seeing the green like I am, but that is absolutely fluorescing like a greenish yellow color. You can tell it's a lot more green than blue, and it's a lot more green than it was when I first put it in here when it was white. It looks like I got a mess to clean up because some of the dye is kind of here on the side of the flask. Let's try to get it in the fluid here. Come on, baby, get into the fluid. Oh, fluorescence is wonderful. What is the carrier liquid? So, Peter, the carrier liquid is just the contents of a white light stick. That's all I used. All right. So I'm really happy about that this worked. I'm a little weirded out that the phycocyanin didn't work. I guess for whatever reason it's unable perhaps to pick up the energy in this reaction, but boy, the curcumin just really, look at that greenish color that we shifted this by adding a different dye to the white light stick mixture. Oh, that's beautiful. And the other thing we can do here, okay, here's I got a control in our back so we can kind of get an idea of how brightly these are, chemiluminescing. And what I can do here, sorry I keep turning on the light, but I got to see what's going on. It is a nice cyan green. This chemical reaction, this chemiluminescent chemical reaction, is catalyzed. What that means is it's sped up by a catalyst, and the particular catalyst that speeds this up is base. So what I'm now going to do, I'm going to add some base to this flask. I have to keep this here as a control because the camera adjusts. And what I'm going to do is I'm going to add a few drops of base over here. And we're going to see if the reaction goes more quickly. And we'll be able to tell the reaction goes more quickly. If it brightens up, of course, a faster chemical reaction is going to release the light more quickly. Why do we need to break the light stick to light it? Great question, Dot. So why do we need to break the light stick? Let me put this in here while I'm answering this question. So you don't want the light stick to, you don't want it to be glowing until you're ready. And so what they do is they take the different chemicals that are present in a light stick. So I've added the base here. Let's give it a swirl, see if it gets brighter. Oh, yeah. So you take the different chemicals that are present in a light stick and you put them in different compartments. Actually, I added acid again like an idiot. I keep doing that. No, that was base. So that slowed it down, which is odd. I don't know what the heck's going on there. Anyway, you put the different components of the light stick into different compartments. One of them is inside a glass ampule. And when you're ready to initiate the reaction, you simply break the inner glass vial, and then the two, well, actually it's more than two. There's 4 components, and the 4 components mix. And then off it goes, there's no stopping it after that. I'm a little weirded out. I don't know why you know what? I think I do know what happened. I added base to this and it stopped chemiluminescing. And I think I know what happened. That's because the curcumin dye that's in here, the curcumin dye that's basically doing the fluorescence in here, it takes on different form at higher pH, and it must be the case that that higher pH form doesn't fluoresce as well. So I screwed it up. Yeah, that's exactly what I did. Well, I don't know what's exactly what I did, but it's a good explanation. All right, I'm going to try to clean this out. We'll try her again. Hello there, Charlie. Great to have you on board. And while I'm cleaning up, why is polonium highly toxic, Bester? It's because it releases, it's an alpha emitter. It's a radioactive substance that emits alpha particles, and those are really not good for you. So here's the overall chemical reaction that powers light sticks. We'll just set it there like this. We'll go over the different parts here in a moment while I clean up this flask. But up there at the top, you see a very large molecule. It's called TCPO. That stands for trichloro. You see the 3 chlorines on each side. 3 chlorines over here, 3 chlorines over here. Trichloro phenyl oxalate. So the phenyl groups, those are those kind of ring-shaped structures. If you're not familiar with chemistry, they might look like eyeballs over here on the side. Those are called phenyl groups. So we have 3 chlorines on the phenyl group, so we call it trichloro. It's actually bis trichloro because there's 2 of them, bis for 2. Bis trichloro. Phenyl, so there's the phenyl group. Oxalate, this thing here in the middle is the oxalate part. This O, C double bond O, C double bond O, O. And that thing reacts with hydrogen peroxide that's in the light stick. And someone asked about why you have to crack open the light stick, and that's because you need to keep the peroxide separate from the phenyl oxalate, because otherwise the thing's going to start glowing. So you got to keep those 2 things separate. And when those 2 things, when they're ready to react, and what happens is, which component was the phenol? So the phenol portion is going to be this ring-shaped structure with the OH, okay? That's the phenol. Now, we'd call this thing with the ring-shaped structure in the OH with the 3 chlorines on it, we'd call that trichlorophenol because there's 3 chlorines attached, okay? So this thing gets snipped up by the hydrogen peroxide into 2 trichlorophenols. There's 2 of them. But that middle portion, it forms this very interesting thing. We call this a high energy. Mercury is poisonous because it reacts with sulfur atoms in your proteins primarily. And it sticks and it's tough for the body to get rid of. Anyway, this is this high energy. We call this a dioxetane dione. You can just think of it as 2 carbon dioxide molecules stuck together. And they don't want to do this, man. They really want to go to carbon dioxide, both of them. Carbon dioxide is a very stable molecule. This is very unstable. Unstable means that it's got a lot of energy if you can get it to react. So what happens then, this dioxetane dione, we're just going to call it the double CO2. That double CO2, it's going to react with dye molecules that are present in the light stick, and this one has a dye that happens to emit a blue color. It'll slam into the dye, and that'll split, the dye splits this into 2 molecules of CO2. But what happens in this reaction is the dye molecule gets some energy. And we just say here, you know, the electrons in the dye molecule get some energy, and we say this, we represent this, I should say, with a little asterisk right here. So we say this is an excited state dye molecule. What's cool about these excited state dye molecules is they don't stay excited forever. They give off their energy. They go back to normal, but they give off light. And the light that's given off depends on the dye. So you can get different colored dyes with different colored light sticks, just like you get different marker colors with different colored dyes and different markers. So what I'm going to do here is I'm going to take this particular light stick, which it looks orange, right? It looks orange, but watch what happens when I mix up the contents of the light stick. It happens to fluoresce white. So the different components, the different dye components that are present in this particular light stick, they happen to give off all the colors of light, and all the colors of light, thank you there, ALT, and all the colors of light, when you give them off, we know this, right? All the colors of light together, it's white. So there's a bunch of different dyes in here, like 4 of them. And to your brain, you know, your brain sees, you know, there's 4 dyes in there, each giving off their own color, but to your brain, it looks white. Now what we're going to do, though, is I'm going to illustrate to you the fact that I can use a different dye to change the color of this. So what I'm going to do is I'm going to take some of this food dye that comes from these natural food colors. We just learned this today, by the way. This is the first time I've done this on a live. Anyway, we're going to take this dye here and we're going to mix it with the stuff in this light stick. And by changing the ratio of dyes in here, we're really going to give it a lot of this yellow dye, okay? And by changing the ratio of dyes in here, we should be able to change the color of this white light stick, okay? Okay, here we go. Let me try to get this done in a way where I'm not going to spray glowing fluid all over my basement. So where's my, here it is. So what I use to cut it open is I use a pair of PVC cutters. You and me both, JM. You and me both. So here we go. I'm going to cut the top off right here. I'm going to try to make sure I don't have, see, I don't want any fluid up there at the top when I cut it. Because when I get fluid up there, sometimes it'll spray. The last thing I want is to spray this junk all over. I gently clip off the top. All right. Then I take this top piece and I put it in a bottle. So I just have a bottle where I just put this stuff in. All right, I can take care of later. So now it looks light blue, but that's because there's some of this business back here. If you look at this, it's kind of like, you're right, it does have like a light blue color. I got a little bit on my gloves here. All right, let's pop this in here. In it goes. In goes our white light stick mixture. No, I don't have any assistants here in my lab with me. I don't have any Jesse Pinkmans with me. Uh-oh, you're going to have to forgive me here a second. It's getting a little messy, so I have to clean up just a bit, okay? Here, I'll show you what I mean. You can see my paper towels here. They're glowing a little bit as I'm trying to clean up. All right? Forgive me, I got to keep it clean as I work. You can see I got a little bit of the light stick mixture on my PVC cutter, so I'm going to wipe that off. Hello there, Rainbow. Welcome aboard. It does smell a little bit. It does have a little bit of a smell. And there, you can see it on the paper towel where I wiped it off. Now this is all, nice and clean. Okay. Yes, that is glass inside. So when you break a light stick, you're breaking an inner glass vial that helps to keep the chemicals separate. You don't want those chemicals mixing, until it's time to light the light stick. Is it toxic? Charlie, I have read articles where people have studied what happens when children eat this stuff. I'm not recommending this, but I do know that doesn't seem to harm the children, but it's not something you'd want to do, say, every day. But if it happens once or twice, certainly call a poison control center, but you probably will be fine. I also had a dog when I was initially doing experiments with these. I had a dog that ate one time. And she didn't like it, of course, but, she was fine. She lived a nice long life, but it's not like I was feeding her light sticks every day. Oh, I'm the same way, Diana. Okay, so now here's the deal. Here's what we're going to do. Remember, I'm going to take some of this yellow colored dye and we're going to add it to this white light stick mixture. And let's see what happens. If I change the ratio of the dye in here, we should change the color because the dye that I'm adding, it should start fluorescing. And it's going to give off its own color that it happens to fluoresce. There's quite a bit in there. Let's give it a swirl, baby. You can see it in there. You see the yellow dye. I'm going to give it a swirl. Come on, look at that shift. Look at that shift to like a green color. There's a lot in there, so it's going to look like yellow from the dye itself. But look up there. You can see it's totally fluorescent green. It's like a yellow green that it fluoresces. Isn't that beautiful? All right, so long. I'm sorry you're taking off there, Roy. Glad to have you along. What is copernicium used for? I don't know off the top of my head. So if anyone wants to Google that for me and drop it in the chat, I don't know off the top of my head what copernicium is used for. Hello there, Timo Chat. I do kind of, JM. My element collection is more what elements have I done experiments with. So yeah, you can see that I changed the color of the white light stick by adding a different dye. And that just demonstrates to you the fact that different dyes in the light sticks are going to give you different colors. And that should make sense because different colored markers give you different colors. You know, it's the same thing, right? It's just that these dyes happen to give off light when they are exposed to the light stick reaction. Isn't that beautiful? Isn't that beautiful? It's looking a lot yellow to me. Definitely looking yellow to me. This is just a white light stick mixture to which I added a yellow dye, and we can certainly see that the white light stick is now emitting a yellow color. Thank you, Hero. And Roy the chemist. Copernicium is a synthetic element, has no uses, so they haven't figured out how to use it yet. Element 112, I know that. Copernicium, oh, thank you, Hero, is a synthetic radioactive chemical element, atomic number 112. Transition. Oh, thank you, Charlie. If I ever eat a light stick, which I do not recommend, by the way, do not recommend eating a light stick. Hello there, Speed Gorilla. By the way, if you'll humor me just a second, I'm going to just flip the camera around and show you real quick. You can see my ugly mug. Oh, so many experiments, so little time. I designed some like goofy experiment T-shirts. And if you like that kind of thing, you might want to check out the link in the description. My favorite one, I got this T-shirt that says only true, what is it? True patriots use Kelvins. You might get the joke. If not, that sure is not for you. Very cool. So what do you guys want to do? I mean, I have a few more light sticks. Drop some ideas in the chat about some things we might try. Thank you there, Timo Chat. Yeah, and what's nice about it is you can pick your own color. I just kind of use the, I just use the tie-dye one because I like tie-dye T-shirts. So W is saying someone did die from an injection. Yeah, I definitely wouldn't want to do that. You definitely would not want to inject this into your blood. Me too, Darren. Me too. Fire? I'm not doing fire. I'm not doing fire, y'all. Oh, so we got Mad Adam. Loves that. I love that shirt too. 1 mole per liter. Hey, Mad Adam, check out the link in my video description for this particular live, and you might see some. T-shirt patterns that you like. You can stick it on a coffee mug, all that kind of stuff. What is this liquid, Bester? Hey, what do you think we show him, huh? What do you think we show Bester what's in this? All right. Here we go. I'm going to pour it out into this back container here. All right. So we'll just pour it out into there. It's just the fluid from a light stick. That's all this is. All right. And we'll do it again. Boy, that's just really glowing a really cool green color. I got some on my glove, so you have to bear with me while I clean up and prepare for the next experiment. I wouldn't, JM. That'd be a really bad idea. Americium is an alpha emitter, and alpha emitters are pretty nasty when they get inside the body. It doesn't stink that bad at all. I don't smell it very much. So I'm going to just give this a quick rinse so that we can see the experiment from the start. Let me give this just a quick rinse, get it cleaned out a bit. All right, and I will put this into my waste container very quickly here. In it goes. All right. Boy, I really got a lot on the side there, so I'm going to have to give this just one more rinse. One more rinse. I think I can get it. There we go. That's what the rinse looks like, by the way, if you want to see it. I'm just trying to get all that gunk off the side as best I can. All right, let's try her again. Back at it. All right, there's our reaction flask. It's not perfectly clean, but it's clean enough. No, I'm not cooking. I don't know. I'm not making any web shooter stuff today. All right, here we go. Oh, before we do this, I like to real quick show everybody the chemical reaction that occurs in a light stick. It looks like bromine without the clouds. So here's a chemical reaction that happens in a light stick. There's a big old molecule in there called, and this is one of basically two that they use. We're just going to pretend it's this one. I don't know in particular which one it is, but the other one's very similar. The molecule, we call it TCPO. It has this sort of, we call this a phenyl ring. It looks like an eyeball if you're not familiar with chemistry. It's just a bunch of, it's a carbon ring in a special form. And you see there's 3 chlorines in it. Right? Chlorine, chlorine, chlorine. And there's 2 of them on each end. So we call this bis for 2, B-I-S, like bicycle. Bis trichloro, you see the 3 chlorines, so there's 2 of these groups with 3 chlorines, so we call it trichloro. Phenyl, that's that sort of eyeball-looking shape, that's a phenyl ring. Phenyl oxalate, so there's 2 of these trichlorophenyls, 1 on each side. And then in the middle, there's this oxalate group. This is the this O, C double bond O, bonded to another C double bond O. And when you react this with hydrogen peroxide, what happens is the peroxide comes in and it snips these phenyl groups off. So you get 2 of those eyeball things popping off. They get cut right off. And here's the interesting part for the light stick. You get this molecule here, which is, it's like 2 carbon dioxide molecules stuck together chemically. And this happens to be a very high energy form because it's much more stable as 2 molecules of carbon dioxide. No uranium here, all right? That's right, Jaggeth. A chemist has entered the chat. This is definitely trichlorophenol. Well done. Okay. So it looks like JM Studios got some americium in their element collection. Anyway, doesn't a phenol have to have a hydroxide? More specifically for Foriokin, it's going to have an OH group, which it's not technically a hydroxide. It's an alcohol group. Those 2 things are slightly different. Actually, they're very different, but you know, to our eye, they look very similar. Anyway, this high energy double carbon dioxide ring, we're going to call it. This is the stuff that powers the light stick reaction. So one of these things that's formed, it slams into one of the dye molecules that's contained in the light stick. All right? Then this reaction splits our high energy double CO2 into 2 molecules of CO2. But that, you know, there's a ton of energy there. Ton of energy that's going to be released as a result of this chemical transformation. And that energy goes into the dye. And we say the dye, you know, the way we represent it, the dye, this is in its unexcited state. This is where its electrons are excited. And we draw a little asterisk here to denote that. So there's a lot of energy pumped into the electrons. Then those excited dye molecules, great to hear there, Jaggeth, those excited dye molecules, they release their electronic energy as light. So they go back to the normal dye state, ready to participate again. But this excited dye molecule releases its energy as light. And a different dye gives you a different colored light, just like different markers give you different colors. Same thing. It's just what's cool about light sticks is the markers give off light. So what we're going to do here is I'm going to show you. Charlie's teacher says, you can eat everything in chemistry, just not everything twice. I love it. I love it. So you can see, right? There's dye molecules in here. Okay? And these molecules that I just showed you previously, they're in separate containers. So there's a glass vial in here. The glass vial usually contains the peroxide. The outer vial contains the TCPO and the dyes. All right? Now when I snap this, that's going to mix the 2 components. Well, actually all the components. And isn't that interesting? The dyes looked orange at first, but when they're participating in the chemical reaction, they look white. And what's happening there is there's actually 4 dyes in here. All 4 of them, when they're mixed together and they're not giving off light, they look orange. But all 4 of those dyes, when they participate in this reaction, they give off a whole host of colors, and your eye perceives that as white. Electrons released from the excited state, baby. We got some chemists in the chat. I love it. Mad Adam, thank you. Okay, now what we're going to do is I'm going to show you that we can actually shift the colors of this by shifting the proportion of dye that's in the light stick. And what I'm going to do, I'm going to mix the white light stick mixture that we can clearly see is giving off like a bluish white light. I'm going to mix it with some of this dye that is found in this type of food coloring. All right? Thanks, JM. Thanks for joining in. Thanks for telling us about your element collection. And we're going to see the color of the white light stick. We're going to see if this can get shifted. So here we go. Here's how I break open the light stick. I take a pair of PVC cutters, and I very carefully, right near the top so the fluid doesn't spray all over the place, very gently, it leaked a little bit. I hate it when that happens. That means I'm going to have some cleanup to do. I'm going to take this and place it in my waste container. And you can see I've got some glowing mixture on my PVC cutter, so I'm going to wipe that off. Sorry I have to do this, but I got to keep things clean. And it's kind of fun to look at this. You know, you can see my PVC cutters are clean, but look at the, look at that. Look at the paper towel I used to wipe it off. All right. Let's give it a go here. I'm going to add. Can I try other colors? Sure, we can try other colors. I know the blue one didn't work. I'm not sure most of the others will work. We can give it a shot. Okay, so in goes the white light stick mixture. This is going to go in my waste container. All right, and that goes. So let's see. I think I can't remember if this fluoresces. This is, I don't think these fluoresce. I know this does because we tried it. You know what? Let's do this. We're going to try neon pink food dye, okay? We're going to try neon pink food dye. Let's just see. Because Charlie the dead girl said, let's try red. I know that this neon pink food dye contains some red. So this is for you, Charlie. All right, in it goes. Let's see if we get a color shift. See if the red dye fluoresces. In it goes. So you can see down there at the bottom. I'm going to give this a swirl, and we're going to hope to see if we get a color shift. Oh, yeah. Look at that. Look at that. We're seeing some, well, I'm not sure. Well, yeah, I think so. I think that is definitely shift to a red color. The issue is that I'm not sure if that color is from fluorescence or if it's just from the fact that the white light that's emitted is going through red dye. I'd need a spectrometer to figure out if that's happening. But you know what? To my eye, that looks red. We're going to call it a victory. It does look like this is indeed fluorescing a different color. Let's see. I'm going to try this. I'm going to add some base, which catalyzes the reaction. Let's see if this glows a little brighter. Here we go. Add some base. Oh, yeah. Come on, baby. Come on, baby. You see that? Oh, that's totally glowing. That's totally giving off orange fluorescence. So I added a little bit of base, which I know catalyzes the reaction. Man, that was freaking awesome. Yep. So the base catalyzed the reaction. Watch it. I'm going to pour it down the side there. You can see it. You can see it. Oh, that's beautiful. That's really beautiful. And what's nice about this is when I added the base to the yellow dye, it destroyed my dye. But here in this case, it doesn't destroy the dye. The dye stays alive, and the reaction goes a lot quicker and gets a lot brighter. Come on, Charlie! Victory indeed. Victory indeed. Thank you there, Nicola. What base am I using? Sure, Jagath. I'm using 20% by weight sodium hydroxide. And we are definitely getting some orange fluorescence. So that orange fluorescence tells me it's not just, from the red dye that's present. I'm seeing a different color than red. And that's telling me that indeed the red dye is fluorescing, which is really cool. What's my favorite color? Hey, everybody in the chat, why don't you drop the heart emoji that displays your favorite color? Mine, man, what is my favorite color? I'm going to have to say blue. I'm going to have to say mine is blue. So they NaOH hydrolyzed one of the previous dyes. I think so, Matt Adam. So what if you're a chemist, you may be able to look this up, or maybe you know it off the top of your head. The previous dye I used was some of this natural food dye that contains um, turmeric, which contains the active ingredient for the fluorescent dye would be curcumin. So I do know that curcumin changes to a different form at higher pH. I don't happen to know if it changes its well, of course it's going to change its fluorescence properties. I just don't know if the fluorescence is completely turned off. Hero's got a light blue. Charlie's got some black, and oh, that's nice. You put two dyes, you can give me two colors or two hearts. Charlie's liking black and red. Jaggeth is saying big time, a black note with some sodium hydroxide. Yeah, I think this has been a little bit of fun. So what I do near the end of the live, folks, is I flip the camera around and I talk to y'all. So if that's not something you want to see, now's a good time to get out of here. I'm going to warn you ahead of time. I'm a 57-year-old man in my basement. So if that's not something that you want to see, now's the time to get out of here. So I think, yeah, at this point I better do some cleaning because I'm getting just a little bit too much glowing stuff around here that I better clean up. Here, I'll show you what I mean. Look at my, oh, you can't see it anymore. You can just see a little bit of glow on my paper towel still. Thank you there, Millie. Thank you, Matt Adam. I appreciate it. Yep. Well, Charlie, I hope you do get some sleep tonight. I don't want to keep you up all night long for sure. So I'm actually glad that you're going to be taking some sleep. And you can see here where I've been cutting the, that's where I've been cutting the light sticks open. You can see a lot of it soaked into a paper towel. So, all right, let's flip this thing around. I should probably clean that up too. We'll flip this around. We'll talk to y'all, and then we'll call it good. All right. So I also want to show you something kind of cool. I just opened I opened a site where you can buy some t-shirts if you'd like to support the channel, if that's your kind of thing, if you like doing that. I'll show you one of the designs. I happen to have it on right now. Let's turn it around. Flip the camera. Here's one of my designs I got. Whoa. So many experiments, so little time. And you can put on whatever color you want. I've got this one on tie-dye because, I want to be flashy on a live. There's no other reason than that. But you can put on whatever color you want. If also you like, if you happen to be a fan of the channel, I can't imagine why folks would want this, but I've got a little design, a Tommy Technetium you can stick on a t-shirt. And if you're interested in that kind of stuff, check out the link that I put in this video description, and you can, head on over to my store and see what kind of things. So Matt Adam has always wanted to play with luminol. I might have to order some. Come on, man. Let me know if you do, Matt Adam. That sounds like fun. Looking drippy. Hero, I don't know what that means. I'm going to take it as a compliment because that's just the kind of guy I am. I always assume the best. So I appreciate the compliment if that was what it was. If you meant something else, then you got to let me know. I can show you some of the other I can show you some of the other designs that we got on the site if you want to see them. There's this t-shirt that's got kind of the Tommy Technetium thing on it. Oh man, Charlotte, I'd love to be your teacher. Of course, you can see this one that's on this t-shirt that I got here. So many experiments, so little time. Life is just too short. There's so many experiments to do. I like this one. I've never had a failed experiment, only new observations. That's what I love about science. The thing about science is you can't fail, man. You just set up the experiment, and if it doesn't go the way you expected, so what? Nature's trying to tell you something. Just pay attention. Look at what's going on, and you can't fail. This experiment was an experiment. What's going on? Tweak it if you wanted to do something different, right? Let's see if I got any others. Oh no, those are the only three I'm showing you. You want to see the other designs? You can go on over to the channel or the site and check it out. You check that out in the in the video description. There's a link. Come on, Matt Adam. A negative result is definitely a result. Absolutely. Oh, it means I got swagger on. Thank you, Hero. I appreciate that. Come on, isn't that true, PA? Sorry, that's what I'm calling you. But yes, when you are curious, life, man, that's so true. when you're curious, life becomes 10 times more interesting. It is so true. And I actually have a t-shirt design that kind of leans into that. It says this. It says, hey, well, it doesn't say hey. It says, the universe is always having a party, and science gets you on the guest list. Think you know what I'm saying there, right? I mean, there's always something cool going on if you just take a little time, pay a little bit of attention, see what's happening. And then what's fun is if you understand science, you can kind of understand what you're seeing and maybe even explain what's going on. And that deepens the appreciation of all the beauty that we get to see in the universe, which is what I think is really cool about science. You know, I love seeing sunsets. I love seeing the blue sky. I love hearing the frogs chirp in my backyard. I love all these kinds of things. I love seeing clouds in the sky. And what's freaking cool is when you understand science, you can not only just feel the awe of the beauty that you're seeing, but in many cases, you can understand to some extent what's happening. And that just deepens your appreciation for all this beauty that we see. Hero has broken 4 phones trying to understand. Oh, Hero has broken 4 phones trying to figure out how they work. So Neura, thermodynamics did that for you. Yes, man. Like specifically statistical mechanics. When I started to finally understand that, it just brought together so much appreciation and knowledge. So Charlie is saying what we learned today: fluorescence dyes are cool. Don't eat glow sticks, and science always has a result. I love it. I love it. Great there, Hemdahl. All right, folks. Well, I think I'm gonna call it a day. I've really enjoyed doing these experiments with you today, probably because it's the first time I've tried them on a live. And I actually did some experiments I've never done before, which is always a thrill for me. And some of them, like we were able to change the color of a white light stick just by adding a different dye, and that should stand to reason that you can do that. It was a lot of fun. I found it beautiful, and I'm assuming a lot of you did too. And I really appreciate you hanging out with me. It's a lot more fun to do these goofy experiments with all of you here. So thanks for hanging out with me. If you want to, get some science swag and support the channel, you can go to the link in the video description. I love you all, and we're gonna see you. I usually do this on the weekend, so we'll see you next week. Tough knuckles. I don't know what that means. I hope it's something good. Why don't we get scrappy right? Oh, sorry, man. Sorry, Lantern. All right, folks. So long. We'll see you next time.